When most people think of finding gold, they picture a scene exactly like this one, a solitary prospector panning in a riverbed, sifting through silt to uncover bright, visible nuggets. But modern industrial extraction requires a totally different approach. Today, gold is locked deep inside solid rock. We're looking for microscopic flecks trapped within millions of tons of unyielding earth. To get from a jagged ore boulder on the left to a pure doré bar on the right, you can't just smash the rock and pick out the pieces. You have to turn that solid rock into fine dust, dissolve the invisible gold into a liquid, and then force it back into a solid. Finding those microscopic specks hidden inside mountains of rock, without losing them along the way, requires a highly specific, continuous industrial pipeline. It is known as the Carbon-in-Pulp, or CIP process. This flowchart outlines a modern CIP plant. We follow the ore chronologically, starting on the far right with physical reduction. Before chemistry happens, massive boulders are fed through jaw and cone crushers, violently breaking solid rock into small pebbles. Pebble-sized rocks drop into a massive rotating ball mill. Heavy steel balls crush them, mixing with water to create a fine slurry called pulp. This physical destruction strictly serves to maximize surface area. By tearing the rock apart into microscopic dust, the process exposes the tiny flecks of yellow gold that were previously trapped inside, making them vulnerable to the chemical reactions. The pulp flows into agitated tanks, where a specific chemical leaching agent is added. This chemical selectively attacks the exposed solid gold, detaching it from the rock fragments and dissolving it directly into the surrounding liquid. Simultaneously, granules of activated carbon are mixed into the tank. Think of these as magnetic sponges. The moment gold dissolves, the carbon grabs it, pulling those yellow particles out of the liquid and locking them onto its porous surface. Combining these two actions in the same tank creates a clever chemical loop. Because the carbon acts as a vacuum, removing dissolved gold, it upsets the liquid's chemical balance. This continuously forces the leaching agent to strip even more gold off the rock to restore equilibrium. So you now have a soupy mix of microscopic rock dust and large gold-loaded carbon granules. Based purely on physical size, how would you go about separating the two? Engineers solve this with a simple physical screen. The microscopic waste rock falls right through the wire mesh, while the larger carbon granules, now carrying the gold, are safely caught on top. We move to the harvesting stage. The captured carbon granules are placed into a hot chemical bath. This strips the gold off the carbon, reversing the absorption, and creating a highly concentrated, gold-rich liquid, known as a pregnant solution. To pull the gold out of that liquid, engineers use electrowinning. Working like electroplating in reverse, an electric current draws the dissolved gold particles out of the solution and permanently bonds them onto solid steel plates, forming a thick sludge. Finally, that thick gold sludge is scraped off the plates and fed directly into the intense heat of a furnace. The extreme temperatures burn away the remaining impurities, leaving behind molten metal that is cast into a solid doré bar. Turning microscopic specks into a pure bullion bar requires absolute control over this sequence. It takes brute physical destruction to expose the particles, chemical dissolution to separate them, and electrical reconstitution to finally pull them back into a solid state. For free milling ores, this highly structured pipeline consistently yields an astonishing recovery rate exceeding 95%.